Hi, my name is Jonathan Behrens, and today I'm going to be talking about efficiently mitigating transient execution attacks using Word. Transient execution attacks, like Meltdown, Spectre, MDS, and so forth, leak information across isolation domains. To maintain security on processors that are vulnerable to these attacks, operating systems use software mitigations. Unfortunately, software mitigations can be quite expensive. Looking at some system call benchmarks from the LEBench suite, presented at last year's SOSP, we can see that the overhead of running with mitigations can be anywhere from a couple percent to several times slower. So, the goal of this work is going to be to provide faster mitigations against transient execution attacks. In particular, our threat model is going to be very similar to Linux, and throughout this talk, we're going to present two main ideas, the Unmapped Speculation Contract and a kernel design that leverages that content. Transient execution attacks come in a variety of forms, but we're going to look at one example attack, in this case Spectre v1. So to lay the groundwork, we're running in the kernel to execute a system call that's been passed an argument from user space. So we've got a memory layout here, which includes an array, a secret that's placed right after the end of the array, and then some shared data structure placed somewhere else in memory. And the idea here is the system call argument should be within bounds of the array, and to check that, we execute a bounds check with an if statement. Now, because of speculative execution, the branch predictor may predict that this branch will be taken even when the system call argument is larger than the size of the array. So if that happens, when we attempt to index into the array with the system call argument, we may accidentally read secret instead, pulling it into variable y here. Now, using the contents of variable y, if we access this shared array and pull the first element into the cache as a result, then we've now loaded y and z, and execution will proceed until the CPU catches up and discovers that actually this if statement body should not have been executed in the first place, and so the values for y and z vanish. Unfortunately, the cache contents do not necessarily get rolled back, so when we return to user space, this process can actually probe the contents of the cache and discover the value of secret as a result. Now, one common way to mitigate this attack is to insert an elfence before that first load. What this does is it prevents speculative execution from passing beyond this line, and therefore halts the attack in its place. Now, the unfortunate consequence of this mitigation, though, is that every execution of the system call, even if no attack is in progress, incurs overhead because the CPU has to pause at this instruction. Now, Word has a different approach. What we do is we unmap the contents of secret, and in fact of all memory that we don't want viewed by user space, when we're executing this system call. Now, execution can pass into the body of the if statement, but when the load is attempted, what we see is that a page fault is triggered, and no memory is actually read. So eventually the processor will catch up, the page fault handler won't actually be executed, and we can take the correct path through execution. But this has also mitigated the attack. Except we don't necessarily have a clear statement of this. So what we do is we describe what we call the Unmapped Speculation Contract. And our goal here is to describe that previous mitigation and say why it's sufficient. So what the Unmapped Speculation Contract claims is that if some memory has never been mapped in the current address space, then the CPU state should be unaffected by the values stored there. And CPU state here refers both to architectural and microarchitectural CPU state. So we think that this makes for a good hardware-software contract, both because most speculative execution can still happen, and it seems that processors are actually able to provide it, as we see from an AMD white paper, where it said, AMD processors are designed to not speculate into memory that is not valid in the current virtual address memory range defined by the software-defined page tables. We don't have a similar claim from other vendors like Intel, but we believe that they should also be able to provide this contract. And so to leverage the Unmapped Speculation Contract, our kernel, Ward, is split into two parts. This is somewhat analogous to Linux's page table isolation, where we have one page table, in this case the K domain, which maps all physical memory in the kernel portion of the address space, and has the user mappings as you would expect in the bottom half of the address space. Then we also have a second page table, second domain we call the Q domain. This one includes the user mappings again, but it also includes a subset of the direct map, specifically only the page table mappings, that we consider safe to expose to user space. Not necessarily safe to modify by user space, but merely safe for user space to access speculatively. Now, let's take a look at this in practice. On the left, we see a diagram of system call execution, in this case traversing a linked list while in the Q domain. And what is happening is, as long as we're only touching memory that's part of the Q domain, we can continue executing in this state. And if that's all that the system call needs to do, we don't actually have to ever map more memory, and we don't have to apply any of the other mitigations that we otherwise would have to. So there's no need to swap page tables, which would be needed to mitigate Meltdown normally. There's no need to flush microarchitectural state to mitigate MDS. And we don't have to run even with retpolines to prevent indirect branches from being executed speculatively, which is required to prevent Spectre v2. Now, not every system call can restrict itself only to the memory that's in the Q domain. So if we attempt to access memory that isn't, we have to enter the K domain. And the way this happens is entirely transparently, where when an access touches memory that isn't part of the Q domain, there'll be a page fault, which triggers a page fault handler that does a world switch. This world switch transitions to the K domain and then resumes execution. So, in more detail, let's take a look at the steps of a world switch. The first step, as we said, is to switch page tables. That's fairly straightforward. The next step, however, is we have to copy the contents of the Q stack to the K stack. For this, I want to give a bit more elaboration. So, it might seem like we could run with the same stack in both cases. The two domains are just in the kernel. They can have a stack. They're not both used at once, so what's the issue? But if we actually look at what's going on, what we're running in the Q domain, everything pushed on the stack is safe to expose to user space, transitively, because the only things that could be pushed onto the stack are things that somehow are gained from memory, and the only thing in memory are things that are safe to expose to user space. However, in the K domain, that's not true. When executing in the K domain, the contents of the stack can contain secrets from other processes or whatnot that are read during execution of a system call or trap handler or whatever. Therefore, we have to be careful that the Q domain's virtual address space, the Q domain's page tables, do not include any mappings that reference the K stack. They can't reference the K stack because if they did, another thread in the Q domain could leak the contents of that running stack back to user space. So we want to keep complete isolation between these two, so we use separate stacks. Now, if the stacks are separate, then how do we make sure that execution can resume between them? And the way we do this here, you can see, is that the Q stack and the K stack actually have the same virtual address. What this means is that when we're executing the Q domain, the instructions that reference the stack, pointers to the stack, and so forth, all point at specific virtual addresses. They continue to work when we're in the K domain, provided that the stack contents remain the same once we switch. So achieving that, actually, is just the memcopy we promised. We do a memcopy during the world switch. And this memcopy actually turns out to be pretty cheap, because the stack is entirely in the cache usually, and we don't generally have very deep call chains when executing in a kernel. And then finally, after we've switch page tables and copy to stack, we can transition back to the K domain and resume executing at the K text. Now let's take a bit more of a look at the kernel text segment, the code that's running in the kernel. So as we were saying, there's shared virtual addresses here again. This is, as we said, important because we're transparently transitioning from the Q domain to the K domain. So the two text segments actually have identical instruction layouts, compiled from the same binary. However, at runtime, we can actually make modifications to them independently. So we have a couple tricks we do. We can patch an L fence and replace it with a no-op. We can patch out other instructions that apply mitigations, all completely safely. And so when we're running in the Q domain, we don't run those mitigations, and when we're running in the K domain, we do. In addition, we want to avoid switching to the K domain as often as possible. So to do that, we have to have as much data in the Q domain as we can. Unfortunately, many data structures have a mixture of secret and non-secret data. And as we know, the secret data can't be placed into a process's Q domain generally. So looking here, we can see a process structure. The first entry is a next pointer for an intrusive linked list. And then we have a process identifier. Both of those don't contain themselves any sensitive information. We don't protect the addresses of items in the Q domain. So what that means is that a scheduler can operate on this structure entirely in the Q domain and without needing any secrets, because both of those are non-secret. Whereas the saved registers, which in the original design were packed right next to those two items, are moved to a separate structure. And what this enables is that separate structure can be placed in a different part of memory away from the public. And what that means is that these sensitive registers, they can contain anything from user process, including saved encryption keys or other sensitive data that's being computed on. So we have to keep those private to the specific process. So those are in a separate structure. Let's also take a look at another subsystem we have, which is related to memory management. While in the Q domain, we're actually able to manipulate the page tables that are in effect. This on itself seems a bit surprising, but let's walk through it. So if we have the physical memory backing the page tables is itself in the Q domain, then we can modify those page tables safely. And the Unmapped Speculation Contract, if you recall, talked only about the current page tables. So it cannot speculatively allow changes to them that are not yet committed to the page tables. So this enables us to do a bunch of powerful capabilities. We can allocate anonymous memory while in the Q domain. We can create temporary mappings if we want to map something and later unmap it while executing in the Q domain. And we can move pages into the Q domain and out of the Q domain without actually having to use any secrets. So the memory subsystem is a hierarchy of different allocators in Word. The one I want to highlight here is that every core has a list of zeroed pages for our zeroed allocator. That zeroed allocator now enables us to do a lot in the Q domain. These pages aren't themselves in the Q domain, so you cannot just access their physical memory from the Q domain. You get a page fault and switch to the K domain if you tried to. However, we know the address that they're located at from the list. And what this gives us is that since we know the pages are entirely zero, and we know their virtual and physical addresses, we can map them into the Q domain and know that we're not leaking any secrets when we do it because we know the pages are zero. So given these zero pages, we can use them for a variety of purposes, including allocating Q domain memory for kernel data structures, allocating public memory to use for other data structures, allocating memory to use for user space, even allocating memory to back page tables can all be done with a zeroed allocator. So, stepping up a bit, our implementation is based on the SU6 research kernel, and it's about 34,000 lines of C++ code, not counting external libraries. We support all relevant mitigations from Linux, and we're actually binary compatible with a subset of Linux's system call API, which enables us to run some unmodified Linux binaries directly on Word. We evaluated a couple different configurations of Word, including a re-implementation of the mitigations from Linux, in some cases directly using mitigation code lifted from the Linux source tree. We implemented the configuration we've described so far using USC-based mitigations, and we also have a baseline where all mitigations are disabled, so you can see relative overheads. So, taking a look at the LEBench performance suite again, we can see, knowing that relative runtime we want as low as possible, if we look at this getPID system call, this is a particularly pronounced case of a system call that is extremely cheap in the kernel, so it is pretty much just measuring the time to switch to kernel space and then back. So what we see is that the overhead from Linux-style mitigations is, actually you can't see it on this graph, but between 6 and 7 times slower than running the baseline, whereas USC-based mitigations are actually only a couple percent slower than running with no mitigations at all. Then we can see there's a couple other system calls here that also have almost no mitigation overhead when running with USC-based mitigations. So this is small mmap, memory mapping a single page of memory, unmapping a single page of memory, or lazily faulting in some memory that's already been mapped. All three of these have almost no overhead with our design, and fairly substantial overhead running with Linux-style mitigations. Then, we also have this context switch microbenchmark. Context switch is one where we're context switching between two processes that are pinned to the same core. Now, the thing about these processes is that they're mutually distrusting, which means that we actually have to apply a lot of mitigations on every context switch. We have to flush microarchitectural buffers, we have to flush branch predictor state, and so forth. The end result is we have very little speed up compared to the Linux-style mitigation case. The only exception here is that we actually are a little bit better on pipes. And then many of the other system calls, as you can see from this graph, fall somewhere in between these two extremes. We also have application-level performance results. So running this Git binary, what we're doing is we run Git status over a very large repository and see the overhead. What we observe is that our design has less than half the overhead of the traditional approach. Now, there's also a spectrum of related work on different defenses, ranging from pure software to pure hardware, which I encourage you to take a look at the paper to see discussed in detail. But for now, I want to highlight one particular line of related work, which is Intel's Cascade-like processors. These processors have hardware mitigations for many attacks. What that means is that there's almost no need, or there is no need, for software mitigations on these processors. And it actually works out that toggling the mitigations on and off is almost free. But what we also observed on this processor is that the performance of running LEBench Syscalls was up to 33% slower than when we ran with a 2016 CPU model, also from Intel, with the same clock speed and core count on a server that was very, very similar to the one we were evaluating for the Cascade-like processor. So, in conclusion, the Unmapped Speculation Contract defines a division of responsibility between hardware and software, and then using that contract, we implemented Ward, which reduces the performance cost of mitigations. All of our code is available online at GitHub. We encourage you to take a look. Thank you for watching.